Hello everyone, today we'll discuss chapter 1, engine types and their operation. This is the content of this chapter, so we will have a quick look on the history of the engines and then engine classification, engine basic geometry, and then engine cycle, and the last topic for this chapter 1 we'll talk about the fuel. Let's start with an easy topic of this chapter 1, namely historical perspective. The purpose of combustion engine is to convert chemical energy into useful energy, in this case mechanical energy. There are two types of combustion engines from the combustion location perspective. The first type, it's called internal combustion engine. So in this case, the combustion process occurs inside the engine and the working fluid is the mixture that is burned. The second type, it's called external combustion engine. So in this case, the combustion process occurs externally. A simple example of this external combustion engine is a steam engine. The feature on the top right side is showing a schematic of steam engine. So in this case, we have steam entering from this side. So the combustion process or the combustion chamber is not shown in the schematic. And then the steam entering this chamber. So initially it has a high pressure and temperature, so that it's push the piston to the right, and then by a certain mechanism the piston move back to the left, and then the lower pressure and temperature steam exit the engine through this side. So this is a simple example of steam engine, and it's this external combustion engine because the combustion process occurs externally. Looking at the history of the engine creation, the first engine is a steam engine, and it was invented by James Watt. And then later on, an internal combustion engine was developed. The first marketable engine was invented by J.J.E. Lenoir. So this is the gas engine. So gas engine means that the fuel is in gaseous phase, like natural gas. This first engine operated at atmospheric pressure. So in this case, the first part of the stroke take a mixture of gas and air into the engine, and then the combustion process occurs during the second part of the stroke. And then the piston hit the bottom side of the chamber and then move up again doing an exhaust process. So this is a kind of the two-stroke engine. So 5,000 engine was built between 1860 to 1865, and the first engine here has a power of 6 horsepower. So it's quite small power. Okay, and the efficiency is only 5%. So that means 95% of the energy inputted to the engine is going into loss. So it can be to the heat transfer or exiting the engine along with the exhaust gas. And then later on, a new engine was developed by Otto and Langen. So you will know Otto, this is the guy who invented a gasoline engine. And in 1876, first four-stroke engine was developed. And then at that time, about 50,000 engines sold out in Europe and in the US. So four-stroke engine. So it is a gasoline engine, so a spark-ignited engine. The four-stroke engine developed by Otto improved the previous engine version developed by himself, M. Langen, significantly. This table is showing the comparison of the engine, so in terms of the performance and size. So the first column here is showing the performance or engine characteristic from the first version, and this is the characteristic and performance from the four-stroke engine. Both engines have the same horsepower, so 2 horsepower, but this new engine has a much lighter weight, so Mr. Otto was able to reduce the engine weight from 4,000 pounds to be only 1,250 pounds. The piston displacement also reduced significantly from 4,900 cubic inch to only 310. And then you can see in here the engine speed increases. And then another interesting thing here is that on this four-stroke engine, the power stroke per minute increases. So it means Mr. Otto was able to operate this engine at higher operating speed, and then mechanical efficiency increases from 68 to 84, and the overall efficiency increases by 3% in a point, so from 11% to 14%. And then the expansion ratio drops from 10 to 2.5. So looking at this figure, Mr. Otto was able to do an improvement. So in terms of the engine efficiency, makes the engine smaller, makes more compact, and for sure it get a higher acceptable to the market. In 1862, France issued a patent to Mr. Rocas, and he has proposed 4 recommendations. And this recommendation is in line with the four-stroke engine principle. The first recommendation is the largest possible cylinder volume with minimum boundary surface. What does it mean? So we need to maximize the volume. So it's mean the engine will produce higher power or higher work. So you know that work is P dV. So if you can increase dV, then you will have higher work with a minimum boundary surface. So it means with a smaller area, and this is related to the loss of the wall heat transfer. So you know that the heat transfer is a direct function of area. So A times H times delta T. Okay, so if we minimize area, then we also minimize Q. This means we also minimize the losses. Okay. And this first recommendation is still valid till now. So a lot of research is using this recommendation on how can we minimize area, how can we design the piston, how can we design the cylinder head to have a lower surface area. The second recommendation is the greatest possible working speed. So this is also related to the engine output power. So we know that the power equals to torsion times engine speed. For a constant torsion level, if we can increase or we maximize N, so we also get a higher engine output power. Okay, still valid till now. Number 3, the greatest possible expansion ratio. So the popular term on this one is the compression ratio. So if we can increase the compression ratio, so we will be able to get an improved engine efficiency. So you know in Thermo 1 that the thermal efficiency of internal combustion engine is a function of compression ratio, R, and gamma. I think this is specific heat ratio, Cp over Cv. Number 4, the greatest possible pressure at the beginning of expansion. So this is also the idea of having a higher compression ratio. If we have a higher compression ratio, the pressure will be higher, then it will produce higher work. See here, W equal to P times dV. This is also the idea of having turbocharger in the engine to increase the output power. So if we have higher pressure at the beginning of the intake stroke, we will have higher pressure at the beginning of the compression, which results in higher pressure at the beginning of expansion stroke, and thus higher W, higher work. Okay, so this is a very good recommendation from Mr. Rokas, and he proposed this recommendation in 1862. So this predates the finding of Mr. Otto. But because he never realized this recommendation to practice, and we have a consensus that Mr. Otto is the inventor of spark ignited engine. So therefore a gasoline engine, which is a spark ignited type engine, is also called Otto engine. Okay, from there was a further development of the engine, and then there was a two-stroke engine proposed by Ducal Clark, and then as well as by James Robson. And then this is also another finding by Mr. James Atkinson. So they discover, or they invented, Atkinson cycle. So in this case, we expand the engine as much as we can to get a higher engine power. And then the first large engine was built, I think it's around also 1900, and this engine has the bore size of 1.3 meters. So you can imagine 1.3 meters. You can multiply it by 3 to convert it in feet. Okay, and then those engines has a power of about 600 brake horsepower. So I'll explain to you what's mean with the brake, because we have brake horsepower, we have indicated horsepower, I think in chapter 2. And then the engine operated at 90 RPM, so still low engine speed. So with the development of the engine, there is an issue. So the issue at the time was what's called knocking. So you know what's mean with knocking, right? So this is the auto ignition inside the engine when the pressure and temperature is high enough and the fuel can auto ignite. So it's mean it ignites by itself. It doesn't require the external ignition, for example, from the spark plug. Until around 1890, the developed engine was based on spark ignited engine. So it's mean it required an external ignition, so in this case spark plug. And then in 1892, the German engineer Rudolf Diesel outlined in his patent a new form of internal combustion engine. We call this one as diesel engine till now. So in this case, he operated the engine at much greater compression and expansion ratio. So in such a way that the temperature and pressure at the end of the compression is higher, and then the ignition temperature of the fuel, so that the fuel will ignite by itself. So it's mean it doesn't require an external ignition. So you wouldn't see spark plug in diesel engine. So however, it took around 5 years to develop a practical engine of this compression ignition engine, or a diesel engine. So because he is the inventor of this engine type, it's also called a diesel engine. And then in 1957, Mr. Wankel invented a new engine type. It's called also Wankel engine. So this is a rotary engine. So previous engine is a kind of reciprocating type engine. So in this case, the piston move up and down. So in this Wankel engine, the component of the engine rotated about the shaft at the center of the engine, so that we don't have any rotating component. So a good thing for this rotary engine is its compactness, and it's also simpler because it doesn't require a valve train system and so on. But the disadvantage of this rotary engine is its higher surface area, and you know that higher surface area increases the wall heat transfer and thus a lower engine efficiency. And then the anti-knock effect of tetraethylate was discovered at General Motors in 1923. So you know that there was an issue with engine auto ignition, so that we cannot increase the engine compression ratio, so it's just limited at a certain number, because otherwise we have engine auto ignition and it can damage the engine. And then GM discovered this species that can be used to diminish knocking. Since then, a lot of engines and vehicles were built and sold to the market, and it's come to the second problem. This is emission problem. So this table 1.2, is showing a typical emission or pollutant from an internal combustion engine. So the first pollutant here, it's coming from NO and NO2. Usually it is lumped into one species called NOx. Okay. The second one is carbon monoxide, CO, and then unburned hydrocarbon. So unburned hydrocarbon is mean that the fuel that is not burned in the engine and then going out of the engine along with other exhaust gas. And the next one is particulates or soot. So this is the typical emission from a diesel engine. And the next column here is showing the impact of this emission. So NOx, this is toxic. And then carbon monoxide, this is also toxic. And then unburned hydrocarbon, it's generate photochemical smoke. And then this is also the bad impact of particulate. And the next column here is showing a typical emission number from a different source. So this is a mobile source. And then the next column here is emission from automobile emission. So in this case, a spark ignited engine. So you can call this a gasoline engine, although you already have a spark ignited engine using a natural gas fuel. So this number is showing the emission before the after treatment system is applied. So it's called pre-control here. And this is the typical emission number from the current technology. So after applying an after treatment system, NOx, for example, it's about 0.03 gram per kilometer from this SI engine. It is higher for diesel engine, compressed ignition engine. So it's 0.25 gram per kilowatt hour, but it's a different unit. But I believe NOx from a diesel engine is higher than the one from spark ignited engine. And this is the number for CO. So for spark ignited engine, usually it produces about 2 gram CO per kilometer. In diesel engine, because usually it's operate with lean mixture. I think you remember in Thermo 2 what does it mean with the lean and rich mixture. So lean mixture, it's mean we have more air in the combustion. So because of lower fuel or higher air amount, we have a much lower CO in the diesel engine. It has also a lower unburned hydrocarbon compared to the one for spark ignited engine. And particulate or soot, this is a typical emission from diesel engine, so that it has much higher soot compared to the spark ignited engine. So because of this emission problem, a lot of country has been discussing about how can we control this emission to make the life better. And the first emission standard was applied by California state. So this is in 1960. So from that, then another standard was applied as well in the United States, and then in Europe, Japan, and so on. There are many different types of internal combustion engine outside there, and they can be classified by application. So in this case, we have engine for truck, locomotive, and then marine, aircraft, portable power system, as well as power generation. It can be classified by a basic engine configuration. So in this case, we have a reciprocating engine, like engine in your car, or also rotary engines, the Wankel engine. It can be classified by working cycle. So we have 4-stroke engine and 2-stroke engine. Can we have 6-stroke engine? Can be, and you can Google it. Some people is doing research for a different number of stroke, so 6-stroke engine or even maybe 10-stroke engine. But still ongoing there, they haven't proven whether the number of stroke is marketable, but I know there are some people are doing research on this type of engine. It can be classified by valve or port design and location. So in this case, we might see overhead valves, underhead or L-head valves, rotary valve. So we will have a look on this different type of the valve train system, I think in chapter 6. It can be classified by the fuel. So we have a gasoline engine, we have diesel engine, we have natural gas engine, might be also engine with methanol in the future. Can be classified by method of mixture preparation. So in this case, we have carburation. So this old engine, or even your lawnmower engine, they still use a carburetor to mix air and fuel before entering the engine. So it can be a fuel injection into the intake port. It's called PFI, port fuel injection, or it can be a direct injection to the cylinder. So you have GDI, gasoline direct injection. These internal combustion engine types can be classified by method of ignition. So we have spark ignited engine, we have compressed ignited engine, so this diesel engine. The engine can be classified by a combustion chamber design. Okay, so we have open chamber. So this is a typical chamber for spark ignited engine. We can also having a ball-in piston. We can have different piston like wedge or hemisphere. It can be also divided chamber. So divided chamber, here you have a main chamber and a small chamber, which is usually called pre-chamber. The engine can be classified according to the method of load control. So we can control the load by controlling the amount of air and fuel. So this is typical for engine with carburation or even with PFI. We can also control the load just by controlling the fuel. So in this typical diesel engine, so the amount of air is uncontrolled, but you can control the load by controlling the fuel amount. It can be also classified according to the method of cooling. So here we have air cooling, water cooling, and so on. So because we will approach this engine analysis from the perspective of the combustion and emission, so we will select this classification according to the method of ignition to be used in this class. So we will have spark ignited engine. So in this case, we have a gasoline engine or natural gas engine, and we have a compressed ignition engine, which is also called a diesel engine. The next one is engine basic geometry. In a reciprocating internal combustion engine, we have a piston that is doing reciprocating motion, and then by this crank mechanism, the reciprocating motion is converted into rotary motion and then connected to the shaft, and finally it goes to the car wheel. So the major component of the internal combustion engine is cylinder head. So this is at the top of the cylinder. And the second one is valves. So we have intake valves that control the mixture of air and fuel from the intake system into the cylinder chamber. And then we have the combustion chamber itself. So this is the chamber enclosed by the piston top surface, cylinder liner, and cylinder head. So this one. And then we have a piston. So this is the main component. So it's doing a reciprocating motion. And then we have connecting rod. So this connect the piston to the crankshaft here. So this is the con rod. Okay. And then we have a crankshaft. So this one, this is the crankshaft. So the basic geometry of the engine can also be classified into subsystems. So for example, we have a power assembly subsystem. So this one. And then we also have a fuel system, so we can see later on. So we have an injector system, so it's consists of the fuel pumping, fuel filter, the injector itself, and so on. We also have ignition subsystem, so we have spark plug and then coil and so on. So we have an intake system, so we have intake port, intake runner, intake manifold. Similarly, we have exhaust system, so we have exhaust runner, exhaust port, exhaust manifold, and ECU, electronic control unit. So this is kind of like the brain of the engine, so it's control everything. There are several important terminologies in engines. First terminology here is called bore. So this is the cylinder diameter. So this is diameter of the combustion chamber, this one. The second one is called stroke. So this is the distance the piston moves in one direction. So it's moved from TDC to BDC. And TDC, or top dead center, here is the piston position where the cylinder volume is minimum. So when the piston is at this position, the cylinder volume is minimum, so only this region. Okay, and then this minimum volume is called clearance. Okay, the next terminology is bottom dead center or bottom center, so people call this one BDC or BC. Similarly, they also call TDC or TC. So bottom dead center is the piston position where the cylinder volume is maximum. So imagine if the piston position at this position, then we have a maximum chamber volume. The next one is displacement volume. This is the volume swept out by the piston as it moves from TDC to BDC. Okay, so the region between this one and this one. This is the displacement. So when you talk with your friend about the engine size or the engine volume, so either 2 liter, 3.5 liter, or even beyond that if you have a Chevy Camaro, so you are talking about the engine displacement volume. So depending on whether you have 4 cylinders, so if it is 2 liter, then each cylinder has 0.5 liter. The next one is looking at the engine component. So I'm sorry the picture is not great here, but hopefully you can see the main component of this reciprocating engine. So you can see here we have 4 piston. Okay, piston number 1 and then number 2, 3 and 4. So we have 4 piston and it is inline. Why it's called inline? Because the axis of this chamber is in one surface. So later on I will show you a different engine geometry. So this is inline, 4 cylinder, and then we have a valve train system at the top of this chamber. So this one is the valve train system. So we have a camshaft, we have a rocker arm, and then we have hydraulic adjuster, and this is the intake valve. So this valve train system control the movement of this intake valve and the exhaust valve as well. Okay, and then other component we have timing belt. So this connect the crankshaft to the camshaft. So if it is for a stroke engine, so the cam rotation will be half of the crankshaft rotation. Okay, and then this is the bottom side of the engine. So we have oil somewhere here, and this one is the crankshaft. So we have crankshaft. Let me turn on my pen. Is stop here. Okay, and then at the top we have air cleaner. So we should have a piping from outside going into the air cleaner, and I don't see a turbocharger here. So we have air cleaner and then going to the intake manifold, and then finally it's going into the cylinder chamber. So this is the cutaway of 2.2 liter engine. So I think it's close to the Ecotec engine by GM, but Ecotec has 2 liter. So this 2.2 liter engine with a 92 millimeter stroke and 87.5 millimeter bore, and the compression ratio is 8.9. Next topic is engine cycle. Depending on the number of engine stroke, for one cycle we might have 2 stroke. If it is 2-stroke engine, we might have 4 strokes per cycle if it is 4-stroke engine, or it might have 6 or 8 stroke depending on the number of engine stroke. This feature is showing the schematic of 4-stroke engine. Shown in this one is a different schematic of the engine depending on the stroke type. So on the first feature on the left side, this is an intake stroke. So in this intake stroke, the piston move toward bottom center. Okay, so move down. So this means that the chamber volume increases and the chamber pressure decreases. So as the manifold pressure, so in this intake side, stay nearly the same, then the mixture of air and fuel, or just air, or the mixture of air and exhaust gas entering the chamber as the intake valve open. So the driver for this inflow is the pressure difference between the intake manifold and the chamber. So let me repeat again, just to make sure that the piston moves down, the chamber volume increases, and thus the chamber pressure decreases. Then there will be a pressure difference between the intake manifold, so somewhere upstream here, and the pressure in the chamber. And then as the intake valve opens, the mixture entering the chamber, okay, and then at some point the piston hit the bottom center. So the piston then move up doing a compression stroke. So during the compression stroke, the piston move up, and then you can see in here the intake valve is closed. So it's mean here a closed system, okay, a closed system. So it's mean control mesh, the mesh stay the same. So there is no mesh flow and in and out during this compression stroke. Therefore, the mixture is compressed by this piston movement toward top center. Depending whether it is a spark ignited engine or compressed ignited engine, then the spark plug will be ignited as the piston approach the top center, or the fuel will be injected as the piston approach the top center. So this is at the end of the compression stroke. Okay, either we'll have a spark ignition or we'll have the fuel injection. So the injector usually at this location. Okay, so in this schematic we have a spark plug on the side of the chamber. So in this one. Okay, and then there'll be a combustion process. Then there'll be a release of the chemical energy into the thermal energy, which result in increase of the mixture pressure and mixture temperature. And then the piston move down, so from TDC to BDC, and doing an expansion stroke. This expansion stroke is also called a power stroke because it is at this stroke the engine generates a power that is transferred to the piston, and then through this connecting rod the power is transferred to the crankshaft and so on and so on, and then it will propel the car wheel, okay, or it will propel the dynamometer wheel, okay. During this expansion stroke you can see in here that both valve is still closed, and then the piston move down toward bottom center, and then at some point before the piston hit the bottom center the exhaust valve open. Okay, so we'll have more explanation about this one. And because the cylinder pressure is much higher than the pressure at the exhaust manifold, although the piston moved down, so it's mean the cylinder volume increases, there will be a gas exiting the chamber because of the pressure difference. Okay, and this process is called exhaust blow down. Okay, so the piston continue its way toward bottom center, and then once it hits a bottom center, then the piston move up again, and this is the exhaust stroke process. So in this case the exhaust gas is displaced from this chamber going out through this exhaust valve, exhaust port, exhaust runner, and so on, and then exiting the engine by this piston movement. Okay, so we will see later on there are two sequence of the exhaust process here. First is the exhaust blow down, and this happens when the piston is moving toward bottom center and the exhaust valve open. Because of the pressure difference, the exhaust gas is flowing out of the chamber. And the second exhaust process is when the piston move up toward top center. So in this case the exhaust gas exit the chamber because of the piston displacement. In four-stroke engine, to have a one complete cycle, the piston need to move down to BDC doing the intake stroke, and then move up doing a compression stroke, and then move down again doing the power stroke, and then move up again doing the exhaust stroke. So this means that for one complete cycle, the engine need to have a 2 crank rotation, which is 2 times 360 degree. So for four-stroke engine, one complete cycle is done by 2 crank rotation. Now let's take a look for the two-stroke engine. This feature is showing the schematic of the two-stroke engine. In two-stroke engine, one complete cycle is done by just 1 crank rotation, and the compression and the expansion process or the power stroke are the same as the four-stroke engine. The difference is on the intake and exhaust stroke. Okay, let's take a look first on the left feature here. So at this condition the piston is moved down. So imagine at some point the piston might still at this position. Okay, so when it is the case, then the piston move down and doing the expansion process or the power stroke. Okay, and then at some point the piston will be at this position, and you can see in here there are two ports here, one port on the left side and the second one on the right side. The one on the left side is called exhaust port, and then on the one on the right side usually called transfer port. So also important here is the difference of the height between these two ports. So you can see here the exhaust port location is slightly higher than the location of the transfer port. So at some point the piston is at this location and the exhaust port open first. Then because the chamber pressure is much higher than the pressure of this exhaust manifold, let's say this is 0, this is number 1, then the exhaust gas will exit the chamber going into the exhaust port and finally leaving the engine. And then the piston continue move down toward bottom center, okay, and at some point the transfer port will also open, okay, and then because the crankcase pressure, so let me put here number 2, the crankcase pressure is higher than the chamber pressure, 0 here, then there will be a mixture flow. So it can be just air or air plus EGR, or can be air plus EGR plus fuel, okay, if it is spark ignited engine. So there will be a flow of this mixture from the crankcase to this combustion chamber. And then you can see also here a special feature of this piston. You can see here, this is the feature of the piston, so that the fresh mixture is deflected up toward the cylinder head, okay, rather than it just going to the left directly. So the goal of this flow deflection is to maximize the scavenging process. So in the scavenging process, the fresh mixture displaces the exhaust gas, okay. So usually we have a special design of the cylinder head that can direct the fresh mixture following this arrow and then going down and displace the exhaust gas, okay. So and then the piston is at bottom center, the scavenging process continue, and once the piston hit the bottom center, it will move up, okay, move up again toward top center, and the crankcase volume increases and thus the pressure decreases. And you can see in here we have a reed spring valve. So this is the inflow port of the mixture of air and EGR or maybe plus fuel, okay. So because the crankcase volume decreases due to the piston movement toward top center, the pressure inside the crankcase decreases, and at some point this intake manifold pressure, let me put number 3, so this P3 will be higher than P2, and then there will be a flow of the fresh mixture going into the crankcase, okay, and then the piston move up and then close the transfer port first, and then exhaust port, and doing a compression process, and then at the end of the compression process, either the spark will ignite or the fuel will be injected if it is a diesel case. So once again, for this 2-stroke engine, for one complete cycle, the crank wheel rotates 1 time, so it's only 360 degrees. So now you can make a simple comparison between 4-stroke and 2-stroke. So in 4-stroke, you will have 4 stroke for sure. You will have 2 crank rotation, okay, for one complete cycle. In 2-stroke engine, you will have only 1 crank rotation. So from the power density perspective, this 2-stroke engine will have much higher power density, but it won't be double, okay, it won't be double. Why? Because of this poor scavenging performance. So imagine you won't be able to displace 100% of the exhaust gas out of the engine, and the same thing, some of the fresh mixture will flow out of the engine along with the exhaust gas. So it means there will be a process, it's called a shortcut process. So in this case, the fresh air will also exit the engine, and this is a direct inefficiency in 2-stroke engine. So if you already have the fuel there, if the spark ignited engine, so it means some of the fuel will exit the engine. So usually the power density is about maybe 10 to 20% higher than the 4-stroke engine. So if you talk about the 2-stroke engine, usually it's very popular in the racing because you just would like to have a high power density and you don't care the engine efficiency. And recently, this 2-stroke engine is also used for large engine, because usually large engine operate at low engine speed, and it is at low engine speed that scavenging process is better. So it will have a higher efficiency of the scavenging at low engine speed. Next one is looking at a different engine geometry. So I already show you an example of the inline cylinder configuration. So inlines, it's called inline because all cylinder axis is at the same surface. So like a GM Ecotec 2 liter, so it's also inline, and then PSA belong to piezo 1.6 liter, it is also inline. Another type of the cylinder geometry, it's called phi. So in this case, the cylinder axis form a phi letter, so showing in this schematic. So this is an example of the phi 6 engine. So we have 3 cylinder on one bank and another 3 cylinder on the other bank. Okay, so this is an example of the phi 6 engine. And then the next one here is an example or a schematic of a flat, or sometimes it's also called opposed. Is sometimes it's also called a boxer engine. And one of the car engine that use this boxer is Subaru. Okay, Subaru use this boxer cylinder configuration. So you can see in here it is a 4-cylinder boxer engine, and then this is the crankshaft, and this is the cylinder head. So you'll have cylinder head somewhere here. The next one is the radial configuration. So you see here we have 7 cylinder in radial configuration, and then we also have a W configuration here. So it's very interesting here. So you have a 3 cylinder here forming a W letter, and then this is a opposed piston engine. So right now it is popular in 2-stroke engine and with a large size. So you can see in here we have 2 piston, and the cylinder head is only 1. So 1 cylinder head is shared by this 2 piston, and this is the crankcase. So once again, this is very popular in 2-stroke large engine that is used for marine application or power station. And this one is a Volkswagen, so W12. So it has 12 cylinder, okay, and it is used by Volkswagen. Next one is rotary engine. So we won't spend a lot of time for this type of the engine. I just would like to give you an introduction on this engine characteristic. So this rotary engine was invented by Felix Wankel, and Mazda has successfully applied this engine types to one of their products. So it's called Norton rotary design. And a good thing for this engine type is its compactness. So it can operate at a very high engine speed with a very good balance. So it doesn't have a reciprocating movement. So it's just a rotation part. So here it is. It's called sometimes called a rotor. And then it also have a high pickup power output due to high RPM. So once again, the power is a function of the torsion times engine speed. So if you increase N, so you will have also higher power, so P here. So the disadvantage of this rotary engine is its poor surface area to volume. So it's mean that you will have a higher wall heat transfer losses through the chamber wall. And it has also higher hydrocarbon emission because of the leak challenge here. So it's mean you need to have a good sealing for this rotary engine, so to have a better sealing between this rotor and housing, as well as the rotor apex and the housing. So it's compact, and it can also have a light weight design. So for the 4-stroke rotary engine, the schematic is shown in this top right figure. So this is the rotor that rotates about the shaft, and then this is the intake stroke, so the fresh mixture entering the engine through this port. And then the next one, we have a compression stroke number 2 here, and this engine has two spark plug, okay, and then at some point the spark plug will ignite the mixture, and we'll have a power stroke here, number 3, and then last one here is the exhaust stroke, and the exhaust gas will exit the engines through this port. So once again, we won't spend a lot of time on this one. This is just the introduction to you. If you are interested on this rotary engine, there are a lot of material outside there, so you can learn it by yourself. Okay, let's go back again to the reciprocating internal combustion engine, and in this slide we will talk in more detail about spark ignition engine. In spark ignition engine, we can have a premix mixture, so this mixture of air and fuel entering the engine, or we might have only fresh air entering the engine, and then the fuel is injected directly to the cylinder during the intake stroke or during the early part of the compression stroke. So another characteristic of the spark ignition engine is it utilizes electrical spark to ignite the mixture. So this feature is showing schematic of this one is compression process, and then at the end of the compression process the spark will ignite the mixture, and then there will be a combustion process here, and then this one will be a kind of the blowdown process. So in this spark ignition engine, the flame propagates from the spark plug, okay, to far reach of the combustion chamber. So this is just showing the schematic of the flame propagation that consume the unburned mixture. So inside this flame will be the burned mixture, and then outside of this flame is the unburned mixture. And then another characteristic of this spark ignition engine is knocking. So knocking here it means that the unburned mixture will auto-ignite. So it means it will ignite by itself because of the increased pressure and temperature. And the temperature is above the ignition temperature. So you have flame here, and then when knocks happen, there will be additional ignition, so ahead of the flame, maybe is at the edge of this chamber. And when it's happened, then it means it's bad. So it means it can damage the engine component, especially the piston. So knock here is an uncontrolled auto ignition of the unburned gas in front of the flame, and once again it can cause a catastrophic engine damage. So we need to avoid this knocking process. We'll talk each of these characteristics in chapter I think starting chapter 6, 7, 8 and 9. Okay. This feature is showing an example of the cylinder pressure and the sequence of the event. So let's start with the top feature here. So IVO here is the intake valve open. So usually the intake valve open before the piston hit the top dead center. Okay, so it is not at exactly at top dead center, but several degrees before top dead center. And then you can see in here the exhaust valve is still open because the exhaust valve closed at this time, and this one is called valve overlap duration. So the intake valve already open, but the exhaust valve is also still open. So depending on the characteristic of the chamber, there might be some shortcut flow. So it means some of the fresh gas might flow out of the engine directly, okay, because of this valve overlap. Why we need to have IVO before the piston hit the TTC? Because we want to maximize the entrance of the mixture to the cylinder. Okay, so we have intake valve closing at this time. So the period between intake valve opening and intake valve closing is called intake process or intake stroke. Okay, and then you can see here that the intake valve closing is several degree or tens of degree after BDC. So it is not right at BDC. You can see here. So this is the BDC point. Okay, Once again, the reason for having this one is we want to maximize the fresh mixture entrance to the cylinder. Okay, once the intake valve close, we start having a compression process. So the piston continue move toward top dead center, and you can see in here the cylinder pressure increases as well. Okay, and then at some point, so several degrees before the piston hit top dead center, the spark will ignite or the diesel fuel will be injected. Okay, I think this one is a characteristic of the spark ignition engine. I should have the same thing for the diesel. Okay, so this is the spark ignition engine. So at some point, so before the piston hit top dead center, the spark will ignite the fresh mixture of the fuel and air. There will be a combustion, and then there will be an increase of the cylinder pressure. So here, so this increases because of the combustion process. And then once the piston hit TDC, it will move down again, going toward BDC and doing an expansion process. So in this case, we have an expansion process from TDC up to here, up to BDC. Okay, but you can see in here, as I mentioned to you in the previous slide, the exhaust valve open before the piston hit the BDC. Okay, so the process between this point, so the intake valve opening up to BDC, is called a blowdown process. So there will be an exhaust exhaust gas exiting the chamber because of the pressure difference between the chamber and the exhaust manifold. Okay, and this is a blowdown process between this point and this point. Okay, and then the second part of the exhaust process is between BC and TC, and the gas, the exhaust gas will exit the chamber because of the piston displacement. So we have the exhaust process from the exhaust valve opening until this point. Okay, until this point. So what's happened with the cylinder pressure if we don't have a combustion? It is shown with this dashed line. So if we don't have the combustion, the cylinder pressure still increases because of the compression, but the peak cylinder pressure will be only at this point. Okay, and this cylinder pressure with this dashed line is usually called motoring pressure. So it means this pressure is only due to the compression process. Okay, and the difference between in this you can see in this feature, the difference of this area is due to the combustion process. Okay, and this is the work that is generated by the combustion process and then transferred to the piston. Okay, and then at the bottom side here is showing the change of the chamber volume. It is normalized by the Vmax, so maximum volume of the chamber. At TDC, so we have a minimum volume ratio here. Okay, and then at BDC, for sure, V over Vmax equal to 1, because maximum volume occurs when the piston at a BDC. And then another chart here is showing the history of the fuel mass. So you can see in here at this point we don't have the combustion yet, so it's mean 100% of the mixture, it is unburned mixture. Okay, and then we have the combustion, and there will be an increase of the burns mass here, and at some point it will hit around 1 here. So it's mean almost 100% of the fuel is burned. Okay, but you will see later on, I think in chapter 9 or chapter 10, that not 100% of the fuel will be burned. So there will be some unburned fuel at the end of the combustion process, and this will be one of the source for the emission. So this is unburned fuel emission. How is the fuel introduced into the engine? So there are a different type of the fuel introduction to the engine. So the old one is using carburetor. So you can check in your lawn mowing. I think they still use a carburetor to introduce a fuel and then mix with air and then entering the engine. On a modern engine, we have different types of fuel introduction to the engine. This feature is showing schematic of the different types of the fuel introduction or fuel preparation entering the engine. On the feature on the left side, so we have what is called a single point injection. So in this case, we have one injector. The fuel is introduced before the throttle valve. So number 3 here is throttle valve. And this throttle valve control the mixture of air and fuel, and thus controlling the engine power. And then on the right side, we have one injector for one cylinder, and it is injected at the intake runner. So this is the intake manifold. So let me put this A, and then this is the intake runner. So this is the passage between the intake manifold and the engine. So on schematic of B here, we have one injector for one cylinder, and this configuration is called port fuel injection, so PFI. So you might see this PFI in car body or somewhere in the engine. So PFI, so it means port fuel injection. So the schematic is shown in this V. And then some of the modern engine introduce the fuel to the engine directly inside the cylinder. So each cylinder has one injector, and once again the fuel is introduced directly inside the cylinder, and the fuel injection occurs during the intake stroke or during early part of the command stroke if you want to have a fuel stratification during the combustion process. And this configuration is called GDI, gasoline direct injection, and this one is called PFI. So for sure, configuration B and C is more expensive than configuration A because you will need more injector, and you know, injector is also pricey here. A good thing of this schematic or good thing of the PFI and GDI compared to single point injection is its responsiveness. So especially for GDI, because you inject the fuel directly inside the cylinder, you can change the load with a very short response. Okay, compared to, let's say, A here, if you change the load, it will take a time for cylinder to respond the change of the fuel, because there will be a delay due to this distance from this one to this one. Okay, but this one will have the best response from the transient. This one will be the second one. Okay, so we will have a detailed analysis of this PFI and GDI in chapter 7. This feature is showing schematic of modern spark ignition engine. So it's only one cylinder is showing here. So this is the engine. So this is the piston, and then we have a spark plug here. And then let's start looking at the entrance, at the intake system. So we have intake system starting from this point, I believe. So this is the entrance of the air, so fresh air, or it can be plus exhaust gas recirculation. And then we have, I think this one is the sensor for the airflow, and then we have some temperature sensor, and then this is the fuel injection, you can see here. So this is the injector of the fuel. I think it is injected before the intake valve, so it is PFI, port fuel injection. And then this is the intake valve, this is exhaust valve. And then next one, I think this one is the ECU. And this one is the fuel tank. So we have the fuel pump inside this one. Let's pump the fuel going up to the injector here. So I think this is the injector driver. And then this is some of the sensor, so it can be like temperature sensor, and then speed sensor, knocking sensor, and then going to the exhaust system. This is the exhaust manifold, and then I think this is some of the sensor can be used to measure the temperature or measure the gas composition. And this one can be after treatment system like three-way catalyst. This one another sensor, and this one can be like a kind of further catalyst part. Okay, so this one is I think several interface that can be changed by the user. Okay, and this one is a pedal. This one is the cutway for GM Ecotec 2 liter. So it has 4 cylinder. So it means each cylinder has a 0.5 liter volume. I think this GM Ecotec is used by, I think one of this is Saturn, I think, use this GM Ecotec 2.0 liter. So you can Google it, which car that use this Ecotec 2.0 liter. So 4-cylinder inline, so it's mean the cylinder axis for all cylinder are at the same surface. The bore is 86, stroke is 86, so you can see here the bore equal to the stroke. Sometimes it's called a box engine. Okay, and then compression ratio is 9.2, and the maximum power is 187 kilowatt or 250 horsepower. And then this is also the data for the maximum torque, and this is the speed at maximum torque. Next one, hybrid engine. This is one of the hot topic right now beside the electric vehicle. So hybrids means that the engine has a conventional engine, either this is diesel engine or spark ignited engine, plus electric motor. Okay, so there are 3 different configurations of this hybrid. So one is called parallel hybrid. So in this case, the engine is connected directly to the drivetrain, the motor as well. So it means both are connected to the drivetrain. So both can drive the wheel. Okay, and then the battery can be charged from regeneration. So regeneration here means that we utilize the energy that is lost because of the brake. So rather than leaving the energy as a loss because of the brake, so we can use this energy to charge the battery, or it can be from plug-in. So that's why we have PHEV, so plug-in hybrid electric vehicle. If it doesn't have a plug-in feature, so it's just HEV, hybrid electric vehicle. Okay, parallel hybrid. The second configuration, it's called a series hybrid. So in this case, the engine is not connected to the drivetrain, rather it is connected to the generator to generate electricity that can be used to propel the motor, and the motor will drive the wheel of the car. Okay, so the battery can also be charged from the regeneration or can be from the plug-in. Okay, a good thing for this series hybrid is that the engine operating condition is independent of the car engine speed or car engine load. So it's mean we can operate this engine at the optimum point. So you will see later on in the next chapters that the engine has a certain operating characteristic. So at some point it can operate at the best optimum point. At other point it will have a very low efficiency. So with this series hybrid, we can operate the engine at the optimum point because the engine operating condition is independent of the required power from the car. For sure, this series hybrid type is more expensive. The next one here is a power split hybrid. So you can see in here the engine can have also direct connection to the drivetrain, and then it can also have a direct connection to the generator that can propel the motor, and then the battery can be from regeneration process or also charging through the plug-in. So this is three different type of the hybrid, and right now we assume that this hybrid technology will be the option in the next 10-15 years because of the price compared to the electric vehicle 100% battery. And we have made a simple analysis that the emission from this hybrid is comparable to the emission of the electric vehicle. So this emission for sure need to consider the CO2 generation when the car is produced, when the car is used, and when the car is recycled. Then you will see that the total CO2 production of the hybrid engine is comparable to the total CO2 production of the electric vehicle, so battery vehicle. This one is showing a schematic of a boosted SI engine. It's called a boosted because this engine utilize a turbocharger, okay, or it can also utilize a supercharger. We'll learn about this different charging process in chapter 7, I believe. So it's called supercharger because the compressor power is directly from the engine. It's called turbocharger because the compressor power is coming from the turbine that is propelled by the exhaust gas energy. So this one is showing a schematic of turbocharger. So we have a turbine and compressor with one shaft here. So the turbine shaft is connected directly to the compressor shaft here. So in this schematic, we have point number 1 where we have the entrance of the fresh air, and then is following this path, and then it goes to the compressor, and then the compressor will compress this gas, increases the pressure, and then entering the engine. Okay, it is through this point, so it's going to the engine through this point. So this is the intake runner. Okay, and you can see in here before entering the engine, the fresh air need to flow to this one, and I think one of this component will be the charged air cooler. So the fresh air is cooled to further increase the amount of air entering the engine. So you know, for the same pressure, if you lower the temperature, we'll have a higher density. So this is the piston, and then combustion chamber here, and then it's exit the engine through this exhaust port, and then it's enter the turbine, and then exiting the engine following this exhaust pipe, and then leaving the engine through this path. Next one is looking at the characteristic of direct injection spark ignition engine. So to have a good mixing process between the fuel and air, we rely on the swirl flow, or the flow pattern of the air inside the chamber. So we will learn this in more detail in chapter 7 about the swirl flow, tumble flow, and so on. So this is an organized flow, so kind of like a bug flow following a certain pattern that can be used to enhance the fuel-air mixture. And also we rely on the piston shapes to guide this spray to have a better mixture with fresh air. So once again, the level of this mixing process determine the performance of the combustion process, and thus the efficiency of the engine. And we might also have a special type of the injector with a wider spray cone angle, also in the C, and this will also improve the mixing process between the fuel and fresh air. Next one is looking at the introduction of the large engine. So large engine is mainly used for marine application as well as the power station, so to generate an electricity. So this is the cutaway of large natural gas fuel boosted SI engine, so used in electric power generation. So the bore size is 170 millimeters, So 170 millimeters, and stroke is 190 millimeters. So 190 millimeters here is 0.15. So I think close to how many feet this one? So this is 19 centimeters. So it's almost 2 feet, okay, the stroke here. And the displacement volume per cylinder is 4.3 liters, okay. So it has 8 cylinders, so the total will be 30, so 8 times, okay, 34.4 liters. So, and the compression ratio is 12 to 1, okay. So this one is from Caterpillar. So you can see in here it is a phi type engine configuration. Next one is the introduction of pre-chamber spark ignition engine. So in this case, we have a main chamber and a pre-chamber. So in this pre-chamber, we have a spark plug. And then depending whether this is active or passive pre-chamber, we might have additional fuel injected or introduced directly to this pre-chamber. If it is an active pre-chamber, so we will have additional fuel directly to this pre-chamber. If it is passive pre-chamber, then we only have the fuel introduction through the main injector or through the intake port. Okay, so this pre-chamber is used to enhance the ignition process, and it is usually used when we operate the engine under lean conditions. So it means we have more air, so to have a better efficiency, but linear mixture required a robust ignition process. Therefore, we have a pre-chamber here to improve the ignition process. This feature is a pre-chamber spark plug. So it is a passive pre-chamber, so we don't have a fuel introduction to this pre-chamber. And this is a product of Tenneco. So I think you can also buy this pre-chamber spark plug, and you can try in your car whether you will get improvement or not. So passive pre-chamber usually is good for a full load operation condition, especially if you drive your car at a high speed. So drive your car through I-410 or I-35. If you use this passive pre-chamber, then you will gain some efficiency. But it has some drawback when operating the engine at part load, because at some point you might have a misfire when using this pre-chamber. So this pre-chamber is one of the hot topic right now. I know one of my team is doing research on this one, on designing a pre-chamber to be able to operate under a part load and a full load operating conditions. Next one is the introduction of compression ignition engine, or it is called a diesel engine. So in this diesel engine, usually it's utilized non-premixed air and fuel. So in this case, only fresh air that is introduced to the engine, or sometimes it is fresh air plus EGR. So this is EGR, exhaust gas recirculation. So this is used to control emission. So it can be a mixture of air and EGR introduced to the engine. So we will learn this EGR role in chapter 11. And then at the end of the compression process, the diesel fuel is injected to the chamber. Because the mixture temperature and pressure inside the chamber is above the ignition temperature, then the fuel will ignite by itself. Okay, and then the combustion process occurs. The flame propagates from this injected fuel plume and burn as a diffusion process. So we will study this diffusion flame in chapter 10. And then there will be an expansion process. The piston moved on toward BDC, doing a power stroke. And then the last one here is the exhaust process. So in this compression ignition engine, we don't have a knocking process. Okay, the combustion process itself is initiated by an auto ignition. Okay, but this compression ignition engine has a problem, which is this one, smoke. Okay, and this is the characteristic of diesel engine. So this diesel engine it has a better efficiency because of higher compression ratio. And you know in thermo 1 that higher compression ratio also means better engine efficiency. And this compression ratio is limited by the strength of the material, which is the material for the piston, cylinder head, and liner. Okay, but once again, it has an issue with the smoke. Therefore, it's required a certain after treatment system to meet the emission standard. And usually, the diesel engine is more expensive than spark ignition engine, and one of these reasons is the expensive after treatment system. In thermo 1, I think you know this PV diagram for the diesel or compression ignition engine. So we assume a constant pressure combustion for this diesel engine. And then for the spark ignition engine, we assume a constant volume combustion process. This is the profile of the volume chain, and then this one is the fuel introduction, and this one is the cylinder pressure, and this one is the rate of the heat release. So take a look. Let's take a look on the first feature here. We have a maximum cylinder volume when the piston is at PDC, but you can see in here that the volume is normalized by VE or VC here. I think this is the clearance volume. So we have a 15 here when the piston is at BDC. So, and then we have IVC at this point, and then you will have a compression process, and then the volume will be minimum when the piston is at TDC, and then it will be maximum again as the piston move down toward bottom center, and we have the exhaust valve opening here. So the diesel fuel is injected somewhere at this point. Oh, you can see in here on the second figure. This is the SOI, start of the injection. This is the profile of the diesel fuel injection. Okay, so it will take a time to hit the maximum diesel flow, and this one is EOI, end of injection. So this showing sometimes it's called red shape of the fuel injection. And then the next feature here is showing the profile of the cylinder pressure. So this is the intake valve closing, and then it's starting doing the compression process. The cylinder pressure increases, and this is the start of injection. And then another thing here, what is important, and this is the point of the start of the combustion. So you can see in here, there is a delay between the start of injection and the start of the combustion. So you inject the fuel, so the fuel needs a time to find where is air, where is oxygen, and then it will start having a combustion. So this is usually called an ignition delay. So the duration between SOI and SOC. And then there'll be a combustion process, and then at some point the exhaust valve open, there'll be a blow down process, and then this one is, this one is end of combustion, EOC, sorry, and this one is EVO. So EVO here is exhaust valve open. So it's mean here there'll be a blow down process from this EVO to BC. Okay. And then if you don't have a combustion, then you will have a motoring pressure. It is shown here as the dash line. So this one is the motoring pressure. And the last features here is showing the profile for the fuel combustion in terms of the burn fuel here. Okay, so this is the SOI, and then we have SOC here, and this is the profile for the release of the heat. Okay, and this usually following the red shape of the fuel, and then we will have a main combustion here, and then at the end we don't have the fuel anymore, and this is end of the combustion. So we'll learn about this profile in more detail in chapter 10. This schematic is showing the diesel spray. So it has one injector here, and then this injector might have 2, 4, maybe 7, 8, 12, 16. We have done this one nozzle, so hole. So it's mean So one injector can have 2, 4, up to 16 holes. So we have done a research up to 16 holes for one injector. And the diesel fuel will exit the injector through each hole. Okay. So imagine if you have a 16 hole, if you see from the top, you will have a 16 spray. Okay. I think I have a slide showing this one. Now I will show you the video of the diesel spray along with the combustion that is conducted using a 3D CFD. So we have two video here. On the left side is the baseline, so it's mean this is the existing engine, and on the right side is our study looking at different pistons. You can see in here we put a notch here, which is exactly at the spray path, and we wanted to see what is the impact of this notch to the diesel spray. And this one is the side view, and this one is top view. And the feature or the contour that will be shown to you is the spray plus the equivalent ratio. I think you have learned this term in Thermo 2, equivalent ratio. So this is the ratio of the stoichiometric air-fuel ratio to the actual air-fuel ratio. And see here the piston move up toward the center, and then there will be a combustion process. You can see there, I think it has around 12 spray here. So, and then the spray hit the piston and then deflected up and down, and then it's going to this pocket region, and some of the fuel will go to the center of the region. Okay, so we will learn this diesel spray in more detail in chapter 10. This feature is showing the schematic of the diesel fuel system. We have the fuel tank at the bottom, and then this is the supply pump, and this drive from engine control the timing of the fueling. And then we have a fuel filter here, and this one is the nozzle is going to the cylinder of the engine. And this is one of the injection system type. It's called a common rail injection system. You can see in here that each cylinder has one injector, and then it has one common rail here. Okay, with this common rail, it can ensure a good fuel distribution among the cylinders. So this is one of the new technology for the diesel injection system. Last topic for this chapter 1 is the fuel. This feature is showing the schematic of a refinery process to produce a gasoline and diesel fuel from crude oil. In this refinery process, the crude oil is physically separated by distillation into various products. And we know our friend petroleum engineering is working on this refinery process, so to do a research, developing a good refinery process to have a good quality of gasoline and diesel. So this is just an introduction. If you are interested in this refinery process, you can find some source in the internet about the detail of that process. Besides gasoline and diesel as the primary fuel, we have several alternative fuel. One is LPG, liquid petroleum gas. So the main species of this LPG is propane. So it is C3H8. The next one is natural gas. So the main species for natural gas is methane, CH4. Compared to gasolines, methane has a better knock resistant because of higher octane number. So we will learn about this knocking and so on in chapter 9. However, natural gas has a lower heating value compared to the gasoline heating value. The next one is methanol and ethanol. So we can produce ethanol and methanol from a corn or other vegetable. So sometimes it's called a biofuel or renewable fuel. The next one is biodiesel. So we can also produce this biodiesel from soybean or other plants. And the next one is hydrogen. Hydrogen can be produced from hydrocarbon or even can be made from water. But we need to, for sure, to spend energy to separate hydrogen from water. The last one is ammoniac. So ammoniac has been researched around 1980 and now is coming back again, I think, because of the CO2 problem. And if you look at on the ammoniac chemical formula, it is NH3. So you expect no CO2 emission from this ammoniac combustion. Okay, we have completed chapter 1. I hope it gives you a good introduction for this internal combustion engine. And in chapter 2, we will talk about the engine design and operating parameters.